In this lecture, we're going to talk about coupling or splitting. And what we find is that the signal that corresponds to a particular proton in the proton NMR spectrum will be split due to protons on adjacent carbons. So you might initially expect all of your signals to just show up as one line like this, but in fact, if there are neighboring protons, it will cause the signal to be split into different types of peaks. And these are all known as the different multiplicities of the proton. If it's just one line, it's a singlet. If it's split into two, doublet, and triplet, quartet, quintet, sextet, and septet. If it's split into more than 7 lines, we typically call that just a multiplet. Also, if it doesn't show a neat splitting like these peaks do here, we'll also refer to that as a multiplet if it's just one we can't easily analyze. Let's take a look at a couple of examples here. And as I said before, this concept is known as coupling or splitting, and it's between hydrogen on adjacent carbons or neighboring carbons. So for example, we have in this first molecule, we have a carbon here and a neighboring carbon here. And these neighboring carbons that are next to one another, those are referred to as adjacent carbons. And what we say is that the 2 hydrogen on this left carbon are coupled to the 3 hydrogen on this right carbon. So that's where the coupling terms comes into play. But then on the spectrum, the signal that corresponds to these 2 protons here will be split because of the 3 protons on the neighbor and vice versa. So that's where the splitting term comes in. So first, let's take a look at the CH2 group. And I'm going to label this as proton type A, and I'll label the CH3 as proton type B. So if we take A and we want to analyze how that signal will be split, what you do is look at how many protons are on the adjacent carbon. So on the carbon adjacent to A, there's 3 protons. It's on adjacent carbon B. From there, we follow what's known as the N+1 rule. And this will tell us how many lines it's split into. N is the number of protons on the adjacent carbon. So you take that number, add 1, and that will tell you how it's split. So in this case, there's 3 hydrogen on the adjacent carbon. So N+1 is going to be 3 plus 1, which is 4. So that's split into 4 lines, and that's called a quartet. So the signal for proton A is going to be a quartet. If we do the same thing for B, B has 2 hydrogen on the adjacent carbon. So then from there, we'll take N+1 is equal to 2 plus 1, which equals 3. So B is going to be split into 3 lines, and that will be a triplet. And that's what you would see in the spectrum for this molecule. All right, let's look at the second one over here on the right. So the first thing you want to kind of spot is there is some symmetry here. So there's actually only 2 distinct types of protons. We have type A, which is equivalent to type A over here, and then we have B right here. So you only need to consider A once. And if you look at A, on the neighboring carbon B, there's 2 hydrogen. So N+1 is going to be 2 from HB, plus 1 is 3, which is a triplet. If we look at B on the other hand, Then on neighboring carbon A, you want to include all of the protons that are around it. So if we look, we have 2 here and 2 here. Even though they're equivalent, that's okay. We're going to count them both. That's 4. So from B, we get 4 plus 1, which is 5, and that's a quintet. Sometimes people also refer to this as a pentet, but quintet's the technical term. Here's an example where we see the spectrum. And again, this hydrogen here in green, on the neighboring carbon, there's 2 protons. So you would do 2 is N plus 1 equals 3. That's a triplet. That means it's split into 3 lines. This tends to be pretty far downfield because the carbon has 2 electronegative atoms. So that really pulls that proton downfield. And here is the triplet that we see. It's actually at about 5.8. And you see that it's split into 3 lines, and that's our triplet. Now, if you look at the 2 hydrogen here highlighted in red, on the neighboring carbon, the one that has the hydrogen in green, there's just 1 proton. So N is 1. So we get 1 plus 1 equals 2. That will split into a doublet. The doublet is 2 lines. And there's our doublet. That, since there's just the 1 electronegative atom, it falls in our typical electronegative range. This one's about 3.7, 3.8. Just jumping back to our first slide for a second, here's our different splittings. And I just want to kind of point out how these peaks trail off from the middle. Meaning, if it's just split into 2, both lines are pretty much the same height. There might be a little bit of variation. But then when you get into a triplet, notice how the middle line is taller, and then the other 2 that go on the outside are a bit shorter. So it kind of trails off in size from the middle. And that's actually what these ratios are listed here. The middle is 2 times higher than the outside peaks. And then a quartet, so we follow symmetry. The 2 middle peaks are about the same height, and then the 2 outside peaks trail off from there. Quintet, we have the middle one, which is the tallest, the next 2, and the final 2. Okay, so that's not a huge thing. You don't have to get these perfectly if you're asked to draw them. Just be aware of how these peaks kind of drop off from the center. There's a few common terms that are used to describe coupling, and really they all mean kind of variations of the same thing, but just to kind of parse out the differences. If you hear the term splitting or spin-spin splitting, this just refers to how a signal in the spectrum is being split due to the neighboring protons. If you hear the term coupling, it's really describing the same thing, but it's just talking about how the protons on one carbon are coupled with the protons on another carbon. So if we have protons on these 2 adjacent carbons, this proton and this proton will split one another in each of their respective signals. So we would say that those protons are coupled. And then multiplicity refers to the type of splitting. So when we say doublet, triplet, quartet, that's the multiplicity. And many times people want to be a bit lazy and not write out these full terms. So a lot of times you'll see D for doublet, T for triplet, Q for quartet. And just to fill in the others, here's your other abbreviations for singlet, quintet, sextet, septet, and multiplet. And some of these, to not be repetitive, we use slightly longer terms as opposed to just one letter. We're going to go through some common features that you see with coupled protons, just to show that there are some variations, but we can usually distill these down into pretty simple things. The most common coupling that you want to look for occurs between non-equivalent protons separated by 3 bonds. So that's kind of the key things to remember here. The protons will be non-equivalent and a 3-bond separation. And a 3-bond separation is what we see with protons on adjacent carbons. So for example, in this first molecule on the left, you would expect, because we have the neighboring protons on these 2 carbons, you would expect this proton to couple with these 2 protons, and both would be split from one another. In fact, this was an example that we looked at earlier. But to show you the actual separation between those, you're actually looking for 3 bonds. And that's what we have here. Here's 1 bond, here's the second bond, and the third bond. So that's a 3-bond separation. Likewise, if we come down here to the compound that has the alkene, we have the neighboring carbons here and here. So we would expect the proton on the alkene to couple with these 3 on the carbon. And sure enough, if you count the bond separation, there's 1, 2, 3. And those are coupled. So this proton on the alkene will be split into a quartet because of the 3 on its neighbor. The green CH3 signal will be split into a doublet because of the alkene proton. This third one's the same thing. It's just easy to miss because it's this aldehyde proton, but it will split because of the neighbors. In fact, once again, here's 1, 2, a 3-bond separation between these neighboring protons. So for that reason, you would expect this aldehyde proton to show up as a triplet, because on its neighbor there's 2, 2 plus 1 is 3. And then if we want to look at the CH2 group, we would expect that to show up as a doublet because of the aldehyde. Okay, the second thing that is common, but you won't see this a lot, especially in this course, but I do want to point out that it is possible, is there can be coupling between 2 protons on the same carbon. That typically occurs in things like alkenes. So both of these are on the same carbon in green. The reason that they couple with one another is because they're chemically distinct. Okay, now the reason they're chemically distinct, this alkene essentially locks these bonds in place. And this proton I'm going to highlight in blue, that will always be on the same side as the chlorine, or what we can say is cis to the chlorine. This proton I'll highlight in red is opposite the chlorine, or trans to the chlorine. And it will always be trans. That makes these 2 chemically distinct. You can always distinguish one from the other by the relative positioning on the double bond in relation to the chlorine. Because these 2 are non-equivalent, they're going to split one another. This is only a 2-bond separation. But the one in red will be split into a doublet because of the one in blue. The one in blue will be split into a doublet because of the one in red. Again, only something you have to worry about for alkenes. Also, this two-bond splitting tends to be much smaller than a typical doublet splitting. So if a typical doublet may show up like this, for this two-bond doublet, they're often much, much closer together. In fact, sometimes so close they almost appear as just a single signal. Right, so something to be aware of specifically regarding alkenes. Third thing is almost a non-feature, but protons separated by 4 bonds, you generally don't see any coupling. So in this case, the neighboring protons here on the CH3 would be 1, 2, 3, 4 bonds apart from the nearest protons. Here they're not coupled. That means this CH3 will show up as a singlet. This CH2 will show up as a singlet. The fourth thing deals with heteroatoms like oxygen and nitrogen. And the fact is you generally do not observe any coupling through those heteroatoms, even though they're adjacent. So here we have a CH2 on this carbon, and you have a hydrogen on the adjacent oxygen. So if that oxygen were a carbon, you would expect these two protons in red to couple with the proton in blue. But that doesn't occur typically through the oxygen. So instead, they're not coupled together. So in this case, the hydrogen in red would just be a singlet, integrating for 2 hydrogen. The OH hydrogen in blue would also just be a singlet. Likewise, that's similar for amines. So we have these 2 protons on this carbon. We have the adjacent nitrogen. And we have the 2 protons on that nitrogen. We don't see any coupling there. So the NH2 will just show up as a singlet. The 2 hydrogen I've circled in red, those would be a quartet because they do couple with this neighboring carbon here in green. And then this CH3 group will be coupled with the CH2, so that would be a triplet. In general, if you have alcohol and amine protons in your spectrum, they'll show up as a singlet, and in most cases, they'll be kind of a broadened singlet. Number 5, chemically equivalent protons do not couple. So that's why when we saw this alkene, the 2 hydrogen on that same carbon were distinct. Because they were distinct, those 2 were coupled. But now if we look at just typical alkane type carbons, like the CH3, you can't differentiate those 3 hydrogen. Those are all chemically equivalent. So they do not couple with one another. They'll only couple with distinct neighbors. So for that reason, those all just, in this case, show up as a singlet. So that's pretty easy to rationalize because that's what we've been essentially doing through all of these examples. If they're equivalent, we don't consider them for coupling. This example here on the right, though, is one that will sometimes give people a little bit of trouble because we do have neighboring carbons. And it's very tempting to just want to say, oh, well, these protons here on the blue carbon will couple with the protons on the red carbon because they're neighboring. But what we see is that these two, or I should say these four hydrogen, are chemically equivalent. The two blue are equivalent to the two in red. You can't distinguish those. Because they're equivalent, they don't couple. They're a single proton type. So that's type A. The one in red are also type A. Since they don't couple, what we see in this spectrum is we're going to see just a singlet, and it will integrate for all four hydrogen. Finally, let's just take a look at a spectrum and go through some of the different splittings. First, the easiest one to point out is the alcohol OH, and it shows up here as this broadened singlet. Okay, next, if we look at this CH2 group, what would we expect that to be in terms of coupling? Well, on the neighbor, which is right here, there's two hydrogen. 2 plus 1 is 3, so we would expect that to be a triplet. Okay, let's also go to this next one and look at it as well. The one in green. Again, we only have one neighbor that has protons, and this has 2. 2 plus 1 is 3. That will be a triplet. So we see two triplets in this NMR spectrum. To figure out which one is which, think about chemical shifts. And the one that is next to the electronegative oxygen will be further downfield. This one is just in the allylic region. So here's the one in blue. Here's the one in green. Okay, if we go on down in the molecule, let's look at this CH2. It only has one neighbor with protons. So that neighbor, we just have one hydrogen, 1 plus 1. This will be a doublet. This is going to be in this region being next to the carbonyl, and that's going to be about 2.5. So that's the doublet right here. Next, if we look at the CH, this is coupled to 2 hydrogen here, 3 here, 3 here. So it's actually going to be 8 plus 1 is 9. We're just going to call that a multiplet. Well, we can find our multiplet that corresponds to that hydrogen right here. And then finally, we have these equivalent CH3 groups. Their only neighbor is this carbon with one hydrogen. So that's going to be 1 plus 1 is 2, or a doublet. And we find that doublet right here that integrates for the 6 hydrogen. That's why it's so tall.